Okay, we'll go through the repeated measures ANOVA, walk through the example, some of the reasoning and the logic behind the repeated measures design. Okay, so I'm working with my omega-3 study, and what I'm looking at is I want to see, this was from the t-test actually. So when we did the t-test for words read per minute, if I have 2 times, so the study is eating omega-3 eggs, 3 eggs per day for a month, improves cognitive performance. And cognitive performance is, in this case, can be measured by words read per minute. So how fast can they read with comprehension? So there's comprehension tests, but we don't talk about that. So I measure their words read per minute at the start, pre-test, and then a month after eating the eggs, post-test. And what I'm hoping is that their ability to read, they actually read faster after eating the omega-3 eggs. Right, so this is a simple t-test. I have my data collected over here. I deal with the difference scores, right? So we've done that last semester. We reviewed it at the start of this semester. So it's relatively straightforward. Key thing is each person serves as their own control. So what I'm looking at is I'm looking at the difference scores. I don't care what their baseline is or how they did on average. All I care about is the net difference from time T1 to time T2. So as long as their words went up, but from T1 to T2, I'm happy. I don't care if they were started off at reading 10 words per minute and went to 20, or if they read at 100 words per minute and 110 words per minute and then went to 120, right? The net difference is still 10 words per minute in neither case. It's the net that I care about. Individual differences get washed out, right? So that's the t-test, the dependent means t-test. I can now extend my study, and what I want to do is I want to do the omega-3 egg study, see if it affects people's reading ability in terms of how fast they can read. But I'm doing it at pre-test, but at 3, 6, and 9 months. So I'm doing it now as a repeated measures, but I don't have two periods in time when I'm measuring. I've actually got 4 periods. I got my pre-test, and then at 3 and 6 and 9 months. So I'm really measuring them 4 times in time. Now, once again, I wouldn't do a whole series of dependent means t-tests here. So we'll do a one-way analysis of variance, but this one is going to be special because it's a dependent means or repeated measures analysis of variance. So I run my study. I have 5 subjects in the study, and I get them at pretest, measure their words read per minute for the 5 people, get them on the egg diet. After 3 months on the egg diet, I come in and test their reading speed, do it again at 6 months, and then again at 9 months. Okay, and here's my data. So I have 5 subjects, pre-test, post-test 1, 3 months, post-test 2, 6 months, post-test 3, 9 months, right? So I've measured them 4 times, pre-test and then 3 post-treatment times. Okay. And here's the averages. There looks like there's a steady increase in the words read per minute from pre-test to 3, 6, and 9 months. Okay. Now, the key thing here is it's just like the dependent means t-test. With the dependent means t-test, I look only at the difference scores. The same thing for analysis of variance. The only thing is it's just a little trickier, right? We now add in, as we'll see, we add in one more row to our source table. And that row is the one that takes care of the individual differences, where I don't care where you start from in terms of your word reading. All I care about is the change from one time period to the next. You can go up by increments of 10 from 100 to 110, 120, 130, or you could go from 10, 20, 30. I don't care. They're all, for both, one reads a lot faster to start with, but they both are incrementally increasing by 10 words per minute over the time periods measured. Okay. Okay, so I have my between treatments, right? This is my post-treatment, my pre and 3 post-treatment period, 3, 6, and 9 months. And I also have my within treatments variance. Now, when we did the one-way analysis of variance with between groups, that was simply our within treatments, within groups, our error. Now, with analysis of variance repeated measures, my within treatments is actually split into 2 pieces. There's the piece that's due to my each subject serving as they're in control, the point being that I don't care where they start from. All I care about is the net change from one time period to the next. The not caring where they come from or start from, that's referred to as between subjects within treatments. Then what's left over from the within treatments is the error. Now, the key thing here is what the error is, and what I'm assuming is there's randomness in terms of how much people change from one time period to the next. Subject 1 may increase by 3 words per minute from T1 to T2. Subject 2 may improve only by 2 words per minute or go negative. Actually got slower by 3 words. As long as my error is fairly random, I'm happy. And that's my error variance. Now, where I can get into trouble is, and we'll see later, much later in the lecture, is if the error is the same. Like if people are basically roughly increasing by the same amount, everybody, then my whatever error I have is going to be there's a pattern to it. So I could have a lot of error variability between T1 and T2, but no error variability between T2 and T3, where everyone basically incrementally increases the same. When I start having that problem, I start to violate the assumption, which is an important assumption in analysis of variance, that my error is random noise. If I can detect any pattern to my what's supposed to be random noise, I've violated an assumption of the analysis of variance, and I get myself into trouble. Okay. Now, my within treatments variability is broken now into 2 sums of squares. The between subjects, that being how people do on average, basically they're kind of like baseline, and then what is my true error, the random noise that's in my study. So the within treatments breaks into SS between subjects, SS error. So now I've got really 4 sources in my analysis of variance. I got my between treatments, which is the one I want that variability to be fairly large. I then have my 2 within treatments, my sum of squares between subjects, everyone's baseline, wash that out, and then my true error, the random noise. And then the final piece of variance source is the total, right? So I've got between treatments, between subjects, error, total sums of squares. So I've got that added row added to my source table. Okay, so just once again, just a graphic, total variability between treatments, within treatments, between subjects, individual differences, error variability, random noise. This is the numerator, right? I want to see how much bigger my between treatments variability is, how much of an impact is measuring them at 3, 6, and 9 months, or in pre-treatment, how much is the variability in my total sums of squares due to this as opposed to the error, and how much larger is my between treatments variability compared to my error variability. So it's analogous to the one-way analysis variance. The only difference is what source I'm using for my denominator, right? Okay. Okay, calculations. The between subjects is basically what I do is I calculate the average words read per minute across the 4 times I measured each person. So for each person, I figured out the average of combining their pretest, post-treatment 1, 3, 6, and 9 months. So for example, for subject 1, their average in the study was 66. Then what I do is I take their mean, each individual mean, so it's MN, I subtract from it the grand mean. When I do that, I then square it and multiply it by the number of times I measure each person. So the grand mean is 70. So I take for the first person 66 minus 70, which is minus 4. And then I do that for everyone, and then I multiply it by each of them by the K. Oh, so what I've done is I got the K outside. Okay, so that's I'm just thinking where the 298 came from. So for the first person, it's 66 minus 70 is minus 4. Minus 4 squared is 16. The next person is 6, so that's 36, 16, and 36. And I do that for each of them. Then when I'm done, I multiply it by K. So my between subjects sums of squares is 1192. And that part I don't care about, because I don't care about how people do roughly on average. All I care about is what the net difference is between the 4 times I've measured them. Okay. The error term is really tricky, and it's really ugly because I can't flat out just so. What I'm doing is I'm taking each individual score. I'm subtracting the mean for the person for whom the score is from. I'm subtracting the mean for the time the measurement is from, and then I'm adding the grand mean. So for person 1, it's 56 minus that subject 1's average of 66 minus the 62, which is the mean for the pretest, plus the 70, which is the grand mean. I have to do this funky calculation 4 times. I got to do it 20 times. Not very pretty. Okay, and then there's the between treatments, which is the same as what we've done before. I take each treatment mean, subtract from it the grand mean, square it, multiply it by the number of people, which in this case is 5, and then sum it all up. So the total for the between treatment sums of squares is 520. SS total is simply each individual score by person by time minus the grand mean of 70, square it. So I got to take each of those 20 scores, the 5 people by the 4 times I've measured them, take each person's score across their times I've measured them, subtract the grand mean, square it. And I'm doing this 20 times. And I have it here at the bottom. So the total sum of squares for the whole study is 1,836. Okay, once again, the total sum of squares is partitioned into the 3 pieces. The between treatments of 520, the 1192 that is between subjects, and the 124 that is error. Now what's important is for my analysis of variance, I want to see how much bigger the variance is between treatments compared to error. So the between subjects, once I've calculated sums of squares and degrees of freedom for it, I basically ignore it. And what's important here, and this is what makes repeated measures design so powerful, of the 1836 total sums of squares of that study, a large part of it is actually just the noise that's people differing in terms of how fast they read overall. So that's what makes it. So I'm taking that sums of squares and partialing that out, which makes it, I'm better able to detect small differences with the repeated measures design, because as we noticed with the t-test, each person serves as their own control. Degrees of freedom, relatively straightforward. As we saw, between treatments is the number of treatment levels minus 1. Between subjects is the number of people minus 1. The error term is the between treatments degrees of freedom multiplied by the between subjects degrees of freedom. And then the total, right? K is I'm measuring them 4 times. I have 5 people. 4 times 5 is 20. 20 minus 1 is 19. And then I complete my source table. And my F observed is the 173.3 divided by the 10.3. So my F observed is 16.77. Once again, 173.3 divided by 10.3. Okay, that ends that show. And what I'm going to do is I can walk through the calculations in SPSS or in Excel.